Okay, YouTube, in previous videos we've been dealing with both numerical and variable expressions as well as variable equations, but in this video we're going to confront what happens when we look at a variable equation that contains more than one type of variable. And so that's kind of what we're looking at here. So we're going to be looking at equations that contain more than one variable. We better be using the proper vocabulary for them. So we just call these multivariate equations. And you might surmise, it's called multivariate because it's many variables, all right? But these are actually more common than you would think. As a matter of fact, if we were to write out, say, the formula for the perimeter of a rectangle, which is 2 lengths plus 2 widths, if I had a rectangle look like this, a length and a width, this is a multivariate equation. It's just that sometimes we like to isolate particular values. So not so much knowing that multivariate equations exist as much as we are going to be solving for things in this equation. And it's something that we're not used to doing, like get L by itself and not getting a numerical answer, but getting some other algebraic expression as an answer. So as an example of what I mean, this little warm-up right here, what I want to do is I want to solve this for y. And recall, when you say solve, this means isolate, okay? This is what we want to do. Isolate means to get by itself. Get by itself. And we're going to get these things by itself by using a series of inverse transformations. So when we look at this equation here, we say 7x minus 3y equals 8. Let's think about what we do when we usually solve equations for something we want to know. The first thing would be, let's simplify both sides. And in this case, I don't see any distribution on either side. I don't see any like terms. These are not like terms to combine on either side. So our next step is to get all of the things that we're trying to isolate by itself on one side, okay? We can't have variables on both sides. In this particular instance, we are solving for y. And I notice that y only occurs on the left-hand side of this equation and not on the right. So we don't have to get y's on one side. But now that we've both simplified both sides and identified y and got it on one side, we're going to get it by itself now. So now it's just like solving equations. We say, what do we need to get rid of? And so for the first time, I want you to consider what would you have done if this equation instead said this, 7 minus 3y equals 8. And I said, let's get y by itself. I think the first thing we should do is take care of the 7 and subtract it from both sides. We are going to do the same thing here, except for we don't have just a 7, we have a 7 and an x. So our method is going to be this. We're going to do the opposite of a positive 7x. We're going to do a negative, which, by the way, when you add a 7x to a negative 7x gives us 0, and anything plus 0 is just itself. So we get negative 3y. And on the right side, we're going to leave this alone. These are not like terms, so we're just going to leave it this way. And then the last thing we're responsible for is getting rid of this negative 3 right here. So we're going to do the opposite of multiply by negative 3. We're going to divide by negative 3. And we have to do this to both sides. So I want to say something about this statement. First things first is that we have a denominator that is called a monomial divisor. Okay, we'll talk about this more when we get into polynomials. But mono means one. It just means it has one term. Okay? And if you ever have a monomial divisor, we can split up the numerator, each term in the numerator, so like negative 8/3. I'm going to write that 8 as being the negative and not this 3 down here. And then we got negative 7 divided by negative 3 is a positive, and we get 7/3 x. This is a common practice to do, and we would do this if we were, say, graphing a line. We do that. But it is totally okay also to leave it this way. We'd say negative 8 minus 7x. We'll put this in parentheses. And we'll say all over 3. These are equivalent expressions because they have the same solutions. So if all we're doing is manipulating equations here, the question might be, why would I want to be really good at manipulating equations? And it all kind of comes up to here. Essentially, what I want to do is take some sort of expression, like maybe the perimeter of a rectangle, equation, and plug in values that I know. If I knew W, I could put it here. If I knew, L, we could insert it here, and we could solve for P. So we're going to plug in known values and solve for unknown values. So for instance, when we look at this up here, it says, given the following equation, 2x plus 5y equals 4, I want to find the value of y when x is equal to these three different things. So perhaps we'll start here. We say x is negative 3. I want to know what would I get for y if I plugged in a negative 3 wherever I saw an x. So again, going back to former videos that I've had here, we say plus 5y equals 4. You'll notice that I took out every instance of x, and in this case we're putting in a negative 3. So let's see here. We get a negative 6 plus 5y equals 4. So I say, well, still, I know what x is. X is negative 3. I can find this, negative 3. But what's our y value? Okay, and in order to find this, we're going to have to solve for y. So for instance, I would have to, add 6 to both sides. And so I'd get this, 5y is equal 10, and then we'd have to divide everything by 5 to get y by itself, and we get this y equals 2. So here's what we want to say. We say, when x equals negative 3, then y equals 2. Will we get the same thing if I plug in something different for x? I don't think so. So let's give this a shot. We'll try x equals negative 1. we plug this in again, you notice here that I'm taking out the x, okay? The only thing that I'm plugging in for are x's. And so the same spot comes out. The only difference is instead of putting in a -3, we're going to put in a -1. And we get a different value for our output. So for instance here, I get -2 plus 5y is 4. Of course, what we do next is we would add 2 to both sides. So I would get this 5y's come out to be 6 constants, and we'll divide by 5. And this is entirely okay. What I mean by okay is this. When x is equal to -1, we get a y value of 6/5. And we can leave it that way. You can also call this 1.2. It's entirely up to your discretion. And then last but not least, if we plugged in 2, we say x equals 2. Again, I just want you to see that we're doing the same thing again. We say this is a 2 plus 5y equals 4. And when x equals -2, or sorry, +2, looks like we have 4 plus 5y equals 4. If we subtract 4 from both sides, I end up with this now. We say 5y equals 0. And what I'm really asking is what number could I take times 5 and get 0? And in this case, the answer is 0 divided by 5, which is 0 divided by anything is 0. So when x is 2, we got a y value of 0. So really easily, we can plug in chug. And that's simply it. What I want us to kind of consider, though, is this. I want to do the same task. Wait, so plug all those back in again? That was brutal. But this time what I want to do is I want to solve for y first. And the reason why is because what we're asked to do up here is this. Find the value of y. So somebody's saying find the value of y. Last time I checked, in each of these problems, after we plugged in the x, we had to get y by itself. The question I want to bake here is this. What if we had gotten y by itself first? What if we had been given the original expression? We say 2x plus 5y equals 4 and get y by itself first. Well, what it involves is this. Getting the 2x off of the left side. So that cancels out and we're left with this. 5y equals 4 minus 2x. And then now we're going to divide by 5. So I get this over 5. And so I'm going to admit that y equals this. 4 minus 2 times our input variable all over 5. So if I had done this exercise again, but now I have y by itself, I've solved for y. Now I can just plug in x values right here and get really simple outputs. For instance, we could say, if we were to go back up here and do -3 again, we would say this is 4 minus 2 times -3 all over 5. And you can see here, this is a lot easier. On the top, -2 times -3, that is a 6, positive 6. And on top, I get 4 plus 6 over 5. So I get, let's see, 10/5 is my quotient here, which is 2. And a whole heck of a lot easier to do by solving for y first. So we're going to use the same principle here in this multivariable equation. We say yx minus y is 4. And what I want to do is I want to find the value of x. Find x when y equals these things. And of course we can go plug these values in right now individually. But what I want to do is I want to get x by itself. So when dealing with an equation like this, let's start with that. We say yx minus y equals 4. The first thing you always undo first is addition and subtraction. So we are going to do the opposite of subtract y from both sides. Just like if this were a number, we'll add it to the other side. So I get yx equals 4 plus y. And now we're going to undo our multiplication and division. I notice that y is being taken times my x here. So we're going to divide both sides by y, the entire side. So I just learned something. I learned that whatever x is, it's always equal to 4 plus the y value divided by the y value. So that being said, again, let's go back to what we were just asked to do. It says find x when y equals 0. Now I can just go plug this in. And actually I've got to plug it in wherever I see a y. So both of these spots. But we would say when y equals 0, then we get x equal to 4 plus 0 over 0, which in this case is 4 over 0, which is, this is important, undefined. Okay, so that wouldn't exist for that value. And if we plugged in 3, again, we say x equals 4 plus y all over y, where we're plugging in a 3. And so I get this, 7 over 3, 7/3. So when x is equal to 3, or y is equal to 3, x is equal to 7/3. So that's how you deal with multivariate equations.